So what I've done to prepare for this little review session is I've gone through a couple of your old homework assignments, homeworks 4 and 5, to get some topics that I thought were fairly representative of the major concepts for chapters 4 and 5 that will be covered on the exam. At least that's according to the little checklists that I was provided with. So if I miss anything at the end, if we have any time, then you can go ahead and ask any particular questions you might have, and we can go over some other problems as needed. So as far as what you guys want to start with, we have two options, obviously chapter 4 and 5 concepts. Chapter 4 is things like reflection and transmission of waves, and chapter 5 is waveguides and related topics, waveguides, transmission lines, things like that. What would you like to cover first, chapter 4 or chapter 5 topic?
I think the general
4?
stronger on 5.
Yeah.
Yes, that's fair. Very fair, yeah. I had to go through, when I was resolving all these problems, I was looking at it like, wow, I don't even remember covering a lot of this stuff when I took EM Waves. I was like, eesh, good luck, guys. But let's go ahead and look at homework 4 then. First question that I have, question 1 I thought was good to start with. So question 1, that's homework 5. All right, question 1 on homework number 4. The H field in air just above a perfect conductor is given by H1 equals 3x hat minus 7y hat amps per meter. Find the surface current J sub S on the surface of the conductor. The conductor occupies the space Z greater than 0. So what this kind of looks like in space is we have some big, call it a semi-infinite slab of perfect electric conductor. This is our Z hat, Z direction. Let's go ahead and say this is our Y, and X is coming out of the page. So what it's asking for, it's given that the magnetic field in space is a uniform magnetic field, constant with X and Y and Z, and our H1 equals 3x minus 7y amps per meter. That's what's given. So, anybody have a guess? Like, what would we use to solve this problem? What does this speak of? If we're trying to find the surface current, some arbitrary J sub S on the bottom of this conductor. Yes, precisely what this is, it's a boundary problem. It's a boundary condition problem. And if we remember our boundary conditions for a perfect electric conductor, we have our tangential electric field at the boundary is equal to 0. Our normal component of the magnetic strength is 0. The normal component of our D vector is the charge density. And finally, N cross H equals our surface current density. So yes, that was exactly right. This is the boundary condition that we can use to solve this problem. So we have N cross H1 equals our JS. So JS equals N hat cross this 3x minus 7y. What's our normal vector for our conductor? Anyone want to take a guess? Exactly. Because this is our normal vector. So it's minus z at the bottom of the slab. Minus z cross 3x minus 7y. Z cross x is plus y, so it's minus y 3 minus z cross minus y. Z cross y is minus x. That's minus x 7. So our J sub S is minus 7x minus 3y. Good. And the units for this should just be amps per meter, if I'm not mistaken. Never forget your units, kids. There we go. Any questions on this?
Why would it says like z greater than y is negative?
So the normal vector for z is negative because the space occupied by the magnetic field is in this lower region where z is less than 0. The normal vector coming off of that surface is in the negative z hat direction, because the normal vector should always be the normal unit vector pointing out of the electric conductor. Does that make sense?
Also a normal vector above it?
In this case, well, we assume that the electric conductor occupies all space. That's why I said it's semi-infinite. We just assume it keeps extending in that direction. We only care about what's happening at the bottom of this slab. So in that case, our only unit vector will be in the negative z direction. Pretty good? Any more questions about this? Solid. All right. Then, if it's okay, I'll go ahead and erase. We'll move on to our next question. High five. So next question, question 4. So question 4 asks to calculate the critical angle for a plane wave moving from water into water into air and also silicon into air. So it's a two-part problem. So we have some interface, all right? We have our, we'll call this from water to air and silicon to air. Call this water, air to start. And we're given that the relative permittivity of water is 81. So we have some incoming plane wave, and it has some reflection and some transmission. Good. Now, oh, it seems like you use a little bit of a different notation than I'm used to. My bad. Let me put this in a way that you might see on this. Instead, we'll have water down here, and our light is bouncing this way. And we're only interested in the critical angle. Right, so this will be our theta I, and this is our water, air. Epsilon r equals 1, and here, epsilon r equals 81. So critical angle. Any guesses? How do we approach this problem? Snell's law. That is, in fact, exactly what we're interested in. So in the specific case where we're looking for the critical angle, there's actually just a really simple formula that we can use where sine of the critical angle is equal to K2 over K1. So it's a comparison of the wave numbers. And this ends up simplifying into, if we remember that for, thank you, Neville. For a homogeneous medium, the wave number is just equal to omega square root mu epsilon, where our mu and our epsilon are just going to be, this will simplify to omega over c square root mu r epsilon r. And even more simplified, because we assume that these are non-magnetic materials. So mu r is just equal to 1. Right? So in this case, we have K2 over K1, which will be omega over C times square root epsilon R2 divided by omega over C square root epsilon R1. Since our wave starts propagating in water, that will be epsilon R1. Epsilon R2 is permittivity of air. And what we find here is our theta C will become the inverse sine of the square root, because omegas and c's all cancel, they're gone, of epsilon R2 or epsilon R1, which is inverse sine 1 over 9. Which, when you plug it into your calculator, you'll get something along the lines of 0.1113 radians, or if you're a typical American who likes his degrees, you'll get 3.68 degrees, roughly. Are there any questions about this?
Just to be sure, there's no condition for that equation. So one has to be epsilon, like epsilon 1 greater than epsilon 2.
There is a condition, yes. I'm glad you brought that up. Epsilon R2 must be less than epsilon R1. For this condition, for the critical angle to exist, this condition must hold. And what this implies is a critical angle will only appear if the starting medium is denser than the next medium. Any other questions about this? All good? Welcome, gentlemen, just in time. So there's a part B to this, which is it's exactly the same. It's just silicon into air. So silicon, the only difference here is silicon has a different relative permittivity. So I don't think it's really necessary to cover that if you understand this. So good, I'm going to go to erase. All right. Next question is for question 5. So this question, I thought this was fun. I actually remember this from when I took ECE 3317. This is one of our homework problems. White light is composed of the entire visible spectrum. The index of refraction, n equals the square root of epsilon r, for most materials is a weak function of wavelength lambda, often described by Cauchy's equation, which is as given: n equals some a plus b over lambda squared. Lambda. A beam of white light is incident at 35 degrees to a piece of glass with some a equal to 1.4 and b equal to 6 times 10 to the minus 15 square meters. What are the transmitted angles for color? Violet, blue, green, yellow, orange, and red. And this separation of colors is the dispersive effect of a prism. So this is just a problem meant to show you that some materials, their index of refraction is actually not just a constant, it is actually a function of wavelength light itself, which is something that you'll see more in some of your higher level electromagnetics courses if you so choose to take. That sometimes you have to account for the frequency propagating, not just the material itself. So something that we're given here that was very important comes from the previous question, is this was glass, right? Where is that? Very good. And we're also just given n equals the square root of epsilon r, which kind of just, you know, comes from the previous problem that we already derived that. So we have, again, it's the same formulation as before. Here we have glass in the bottom, and we have our incident angle, our reflection, and our transmission. Now what we're trying to find is this theta t as a function of wavelength. Now, we have theta I equals 35. This is for all cases. And now it's really just a matter of plugging and chugging once we got the right equation. So what kind of problem is this? What equation are we? That's correct. It is in fact a Snell's. Oh, don't look like that, Nathan. Just go for it. Don't bother raising your hand here. You'll get him next time, champ. So again, from Snell's law, actually more generally, more specifically, in equal to into sine theta t. Or this just becomes the square root of epsilon r, 1 sine theta I equals square root epsilon r2 sine theta t. So if we want our theta t, that just solves to sine inverse of the square root of epsilon r1 over epsilon r2 times the sine of theta I. Now, if we remember, this is air, which has an epsilon r equal to 1. So this simplifies to sine inverse of 1 over square root epsilon r2. Sorry. Square root epsilon r1 sine theta I. Now our epsilon ri, r1, is already given, right? So that's just Cauchy's law, or Cauchy's equation. Square root of a plus b lambda squared times the sine inverse, the sine of theta I. And this, we have essentially just formulated our theta t as a function. Now it really is just a matter of taking all the wavelengths and putting them in the, feeding the appropriate ones into the equation, and you'll find that for all of the values we have, let's see if I have space, I'll put the answer right here. Our lambda in nanometers, our N2 value, which I calculate just using the equation, just to show what the trend looks like. We have theta t, which is our final answer. For violet light, it's 400 nanometers. Then blue light is 450 nanometers. Green light is 550 nanometers. Yellow light is 600 nanometers. Orange, 650. And red, 700. When you run this into the equation, yes.
The equation for theta t,
Yes.
we already have square root of
Yes. Yes.
wouldn't that
Wouldn't the square root disappear because it's just a direct substitution of n? Or it could be
This is, remember. Oh, no, I think you might be right. Yes. Yes, you're right. See, I was deviating from the script. Good catch, guys. Yeah, exactly. I was making sure you were actually watching. All right, so it's a good thing. It's a good thing I calculated these in advance. Sheesh. So our n, if we go ahead and just substitute our wavelength into the equation, we end up finding that there's a nice little trend. 4375.4296, 198.167.2.4122. And here, degrees, 76 degrees, 7 degrees. This is 2.66 roughly, 7.7. And of course I rounded here. But you'll notice that there's a really interesting trend. As we increase the wavelength, our index of refraction decreases and our theta t increases ever so slightly. Which I thought was a really cool trend. But anyway, those are the answers. It all makes sense. It's really just a basic application of Snell's law where you have an n that is not constant. Good? Then we shall move on to the next question. Is it okay if I go ahead and erase the board then? You want to take a picture? Go ahead. All set?
Make sure you're getting in the frame.
I'd say try to get my good side, but they're all good sides. Oh, ah. Sorry? Okay.
Complete package.
Keep me on my toes. Make sure I'm paying attention. Hey, I hope they're full. Jeez. I'm not. I'll be confiscating those for evidence.
Is that what we're calling it?
All right, so next question is question 6 on homework. A perpendicularly polarized EM wave travels from medium 1 with a mu1 equal to mu naught and epsilon 1 equal to 4 epsilon naught to medium 2, which has a different set of characteristics. And it wants us to find the critical angle first. So let's go ahead and write that out. I theta r, and here is theta t. And the characteristics we're given is mu1 naught epsilon 1 equals 4 epsilon naught. Mu2 equals mu naught as well. So both materials are non-magnetic. Epsilon 2 is equal to epsilon naught. Good. We'll want to remember these. Now first we want to find the critical angle. So, any takers here? What's the guess? What's our first step? Yes. Yeah. So anybody remember the equation? Bingo. Yes. Very nice. And as we kind of derived earlier, this basically just simplifies to square root mu2 epsilon 2 divided by the square root of mu1 epsilon 1, which even further simplifies when you remember that exactly, yes, mu's cancel. Yes, and the epsilons also cancel. Square root. This is mu naught times epsilon naught divided by mu naught times 4 epsilon naught. Epsilon's gone, mu's gone. This is just inverse sine of 1/2. Very nice, simple formula. Simplification. And if I have remembered my trigonometry correctly from back in the day, then this should solve to pi over 6 radians, or 30 degrees. Pretty straightforward, just critical angle formula. Nothing too special. Part B asks this. If the angle of incidence is 45 degrees, find kx and kz in terms of k naught, which is just the wave number in vacuum. Assume the geometry that was used in class, which is basically just what this is. At least that's what was in the textbook. I assume that's what you also used in class. Is that right? Nice. Oh, I said, I assume this is the geometry you used in class when you were learning this topic. I was just going by what was in the textbook. Nice, good. That saves me a little bit of a... Ah, yeah. Yeah, Z, this should be the normal, shouldn't it? Oh, silly Conlan. See, just making sure you're still awake, that's all. Yes, my bad, that's just on me. Theta R, and finally theta T is this. Yeah. Yes, that is correct. Now, are we okay to go ahead and erase this? I don't remember if we actually need the theta C for anything later, but just in case, we'll make a note up here. Pi over 6 radians. Now, we're given theta I equals 45 degrees. And we need to find kx and kz in terms of the k naught. Boy, my notes are sure messy. So it's nice to remember equations. First of all, these are kind of just the phase matching conditions of reflecting plane waves off of a medium, where kx equals krx equals ktx, kz equals krz. In addition, ktz is equal to square root k2 squared minus kx squared. What else there? Yes, and now we also have kx equals k1 sine theta I, krx equals k1 sine theta r, and ktx equals k2 sine theta t. I think these are all of the really important equations that we really want to know, unless I've missed another one in there, which you'll see on the board shortly anyway if I forgot to write it down. So in this case, it's really just a matter of picking the correct equations to solve for the values that you need. And we'll begin with K1, remembering the definition of wave homogeneous medium is omega times the square root of mu epsilon. We end up getting K1 is equal to omega square root mu naught times 4 epsilon naught 2 omega square root mu naught epsilon naught. And this value is your wave number in a vacuum. That is your K naught. So K1 equals 2 K naught. That'll be helpful. And additionally, K2 is equal, when you plug in its values, omega square root mu naught times epsilon naught, which is just the wave number in a vacuum. So K2 equals K naught. That's great. Now, I'm going to go ahead and that's fine. Just going to have to squeeze in here. Now, we can choose our Kx from here. Because now we have solved for K1, and we're already given our theta I. Now, Kx is one of the values that it asked for. So Kx is equal to K1, which is 2 K naught times sine 45 degrees, which is 2 K naught times the square root of 2 over 2, which is square root of 2 K naught. That is one of the values that we were asked to solve. Now to find Kz, I will need to erase some of this to make space, if that's okay. Let's go ahead and set these up here where our K1 equals 2 K naught and K2 equals K naught. Now, Kz, excuse me. Ah, yes, this is one of the equations that I think I forgot to include. Well, there are more equations that you can find using the phase matching conditions. And the one that we're particularly interested in is that Kz squared is equal to the square root of K1 squared minus Kx squared. This is one of your phase matching condition equations that I forgot to, or at least it's one for it. Now that we have solved for K1 and we have K, we can calculate Z, which, sorry, this is actually Kz squared equals the sum of these squares. But when you, Kz equals the square root of K1 squared, which we calculated was 2 K naught, minus Kx squared, which is square root 2 times K naught. We have 4 K naught squared minus 2 K naught squared. Factor the K naught squareds out. We end up getting K naught square root minus 2. Wow, surprise, surprise. Kz equals square root 2 K naught. Now we have solved for Kx and Kz, and that solves the first part of that question, or the second part of that question. Is there anything that wasn't entirely clear here that I explained? Anything that you'd like me to elaborate on further? All good? All right, cool. Then now we'll move on to part C of the question. And I'll go ahead and move our Kx and Kz up to the top of this, if I don't need these anymore. Well, no, I suppose not. Kx equals square root 2 K naught. Kz, actually, simplify that. Kz equals Kx equals square root 2 K naught. There we go. So part C of this question says, find KTZ in terms of K naught. So it is the z component of the transmitted wave's wave number. So it's the component along this plane wave. And another one of the formulas that I conveniently omitted on accident for the phase matching condition is as follows, where KTZ is equal to the square root of K2 squared minus KX squared. Again, this is just another one of the phase matching. Now we already have both of these values. We've calculated K2 and we have calculated KX previous problem. So KTZ is equal to the square root of K2 squared, which is just K naught squared, minus KX squared, which is going to be K naught times the square root of 1 minus 2. So we actually end up getting KTZ is a complex number, which is what we would expect. And what this implies is that there is going to be exponential decay of this value in the z direction into the second medium. So most of the power, actually all of the power in this wave should be redirected back, or at least the vast majority of it. Now, that's it for that question, actually. So the next, was this clear? Is this good? Yes. So this wave number, knowing that this is a complex wave number, we know that the general formula for our field, let's say our electric field, for a plane wave is some number times e to the minus j, e to the minus, it's kz, yes, not jkz. Yes, that's right, because the j is factored into gamma, e to the minus j gamma, which would be e to the minus kz, right? Right? So having this complex number, we get e to the minus times minus j k naught z to yeah, I'm sorry, I'm blanking here for some reason.
That get it there.
Yeah.
And J stays exponential. When you're taking multiply the a
Yes.
and then you take the part of the j and then you have j in the wave number stays exponential.
Yeah. Okay.
By that, by
The way I'm thinking of it in terms of the propagation constant gamma, because gamma equals minus jk, right? No, it's k equals minus j gamma, right? Is that correct? You haven't. You didn't cover this in mission line.
We haven't gone transmission line.
You've gotten to waveguides?
Yeah, we're doing transmission.
What? Oh, you gotta be kidding me. Oh, okay. Well, I guess if you have any questions on it, then you might want to just ask Nathan after, because I'll be honest, guys, I've forgotten this part. But yeah, the fact that this is an imaginary value, it implies that there's an attenuation. It's probably not a detail you really need to know right now, so don't worry about it. For the exam, just forget about it. It is?
There's a problem
Yep.
in the textbook that's
Yes.
coaxial dielectric.
Okay. Well, let's come back to this. If this is still bugging you guys at the end of the review session, we can answer this later. Let's try to get through some more questions, if that's all right. We will revisit it, though, if we have time. Anyway, the next part of this question, find the distance z naught in the second medium at which the strength is 1/10 the value at z equals 0 approached from the right. Yes, very fun. I'll save our KTZ. I do think we will need this again. All right, so attenuation. I assume you've gotten attenuation, but we'll go ahead and walk through the steps of how we kind of derive that, just for edification. So we have our transmitted wave is equal to some in the y direction times our transmission coefficient times the magnitude of our field times e to the minus alpha z e to the minus j k x x. So it has some attenuation and some phase components, where our alpha is going to be our k naught. And so our initial value, so this is as the wave is traveling, the value that it takes on at the point. This will be equal to our transmission coefficient times the magnitude of the wave, because there's no attenuation has occurred, and we're setting our phase equal to 0 at that point. And as it travels some distance into the medium, T1, we'll have the transmission coefficient times the magnitude of the field again, times some attenuation, minus alpha z naught as it travels some distance, which is going to be equal to this k naught z naught, since alpha is our z naught value. We'll find the attenuation, e t naught divided by e t1 is just going to be our e to the plus k naught z naught, just property of an exponential function. This will be in the denominator. This divides off 1 e to the minus k naught z naught. Put that to the numerator. Now it's a positive sign. And our attenuation, which would be e t1 over t naught, is going to be equal to 1/10. Our strength into the medium over the initial strength, it will be at 1/10 of that value. And so this will become 1 divided by 1/10, just because of how it's been set up. This is flipped, which is 10. Now our k naught z naught is equal to the natural log of 10. And then at that point, it's just a matter of computing this number, flipping around, and finding z naught, which is equal to 2.303 roughly divided by k naught. Is that straightforward? Makes sense, kind of? All right, then, if there aren't any questions about that, there's one more to this problem. Go ahead and save this value. Bye. And you're probably starting to notice the reason I chose this question is because it has so many problems. So, the last part, part E, find the magnitude of the reflection coefficient and the phase shift of the reflection coefficient. Yes, so let's see. Handy dandy formula. I'm not going to go through the derivation of it. You can find that in your textbook. You've probably seen it a million times. For the reflection coefficient, it is actually a complex number. It is mu2 kz minus mu1 ktz divided by mu2 kz plus mu1 ktz. Funny enough, in my intermediate EM wave course, we just derived this again for the first time since I took EM waves. So nice little review from me as well. Now, we've already been given our mu1 and mu2, non-magnetic materials, permeability of free space. Great. Convenient. So this will simplify off to square root of 2 k naught. And by the way, I'm plugging in all these values that we've computed for previous questions. Minus j k naught divided by square root 2 k naught plus negative j k naught. Now all these k naughts will cancel off, and this simplifies to square root of 2 plus j divided by square root of 2 minus j. There we go. We got that complex number. So first we want to rationalize this. So we'll give it multiplied by the square root of 2 plus j divided by the square root of 2 plus j. Once again, what we're doing here to rationalize is taking the conjugate and apply of the denominator specifically, applying it by both the numerator and the denominator to get that complex number only into the numerator. And that will end up giving us, skipping all the steps that we probably don't really care about, 1 plus j to square root 2. This is our complex reflection coefficient. Now what it asked us for was to calculate the magnitude and the phase of the reflection coefficient. Fairly straightforward. Our magnitude, Ri, square root of 1 squared plus 2 square root 2 squared, square root of 1 plus, this is 2 times 2, 8, which just gives us 3. Magnitude I equals, fantastic. These steps pretty clear. I can go and erase some of this. Then phase is going to be equal to, yeah, I'll introduce this concept to you really quick. Our tangent 2, this is just a fancy little function that accounts for the quadrant of each of the arguments. It is probably not on your calculator. So when you do inverse tangents, the reason that you need to be aware of which quadrant your vector is in is it will just give you whatever the division value is. So you give it the y over x. It doesn't give it enough information to say what your true angle is. So if you give this kind of a function the two arguments, the x and the y components of your vector, it will know exactly which quadrant you're in and give you the correct angle. Otherwise, you just need to know where you need to add pi or pi over 2 or subtract whatever, additional number it is. In this case, this is quadrant 1. We have a positive real component, a positive. So arctan 2 of 1, 2 square root 2. This will give us oh yeah, and since it is in quadrant 1, you actually don't care about the phase or the quadrant information. So you could just use tan inverse on your calculator. That would work just fine as well. Just be aware to keep track of what quadrant you're working in. And this would be square 2 root 2 over 1, which both end up giving the same answer, which is 0.392 radians, or 70 0.5 degrees. Any questions on that?
What does it mean exactly for the reflection coefficient to be a complex number?
So what that means is, let's start off with impedances, because that's essentially what this is. Are you familiar with the concept of impedance? I assume from like circuit, right? Where it can be a real or complex number. A real impedance, like a resistance, will just have, it implies energy is being dissipated. An imaginary impedance or complex impedance implies that at least some of that energy is being stored and re-released back into the system with a phase difference. That's why these complex numbers will give a phase. That really just implies a difference in phase. So for a reflection coefficient, this tells you that there is a phase, that there is some energy that is not being, the energy is being reflected in phase. So it's out of phase with the wave. Does that make sense? Yeah. Yes, because this is actually calculated impedances, and you'll see when you get to transmission line that you'll see these reflection coefficients quite a lot. So if that is all good, shall we move on to the next question? Cool. Then, how many more did I choose from? Oh, this is the last one from. So let's go to question 9. Question 9 was fun because it's a polarization question. I figured you'd want to see a polarization question. All right. So question 9. Sunlight contains equal power densities in parallel and perpendicular polarizations. Assume that sunlight is incident at a 40-degree angle on a puddle of water. Because the water is relatively pure fresh water, it is non-conductive and has a dielectric constant of epsilon r equals 1.78. What percentage of the reflected wave power is in the parallel polarization? Additionally, what percentage is in the perpendicular polarization? It seems I forgot there was an additional to that at the very end. If a person is wearing polarized sunglasses which screen out any light which is polarized horizontally, what percentage of the power density gets through the glasses? So let's start with the first question, which is asking how much of that power is in the parallel polarization. So what we're given, our incident angle on the puddle is 40 degrees. And we know both of our media are non-magnetic. And let's see, it begins in air. So this will just be the permittivity of free space. And the puddle of water, epsilon 2, will be 1.78 epsilon r. Epsilon naught, sorry. So we're just going to say epsilon r2 equals 1.78. So we're already kind of given some of the information from question 6. When we calculate our kx, kz, and our ktz, we have the formulas that we need for this kind of a setup. But first, the equation that we want to use for this reflection coefficient is something that should already be accessible. You can find it in the textbook. Formula for parallel polarization, reflection coefficient, is epsilon 2 kz minus epsilon 1 ktz divided by epsilon 2 kz plus epsilon 1 KTZ. So from our, sorry, I thought there was a question for a second. From our previous calculations in question 6, if you recall, that was where we did all that fun stuff with wave numbers. We already showed that kx equals k1 sine theta I, kz equals k1 cosine theta I, and ktz is equal to square root of k2 squared minus kx squared. This is from the phase matching condition, which, if you substitute these this kx in here, you'll find it's equal to the square root of k2 squared minus k1 squared sine squared theta I. That'll be nice and handy in a minute here. So our kz value, since k1 is going to be based off of these values, we see this is actually just k naught times cosine theta I. And then we substitute that into our formula for z, which is equal to now the square root of k naught squared times epsilon r2 squared minus, one second, should be the square root of epsilon 2 squared. I may have made a mistake here in my work. Please bear with me for a moment. We're experiencing technical difficulties. 2 squared. Because k2 should be equal to square root epsilon 2 mu2 is equal to k naught square root epsilon 2. Yes. Yeah, so this should actually be square root epsilon r2 squared minus k naught squared sine squared theta I. Back in business, people. Which gives us k naught square root epsilon r2 minus sine squared theta I. Now we can substitute this ktz, which is comprised of all into our reflection coefficient, which I'll have to rewrite because it seems I solved it wrong in my notes. But I won't show all of the nasty work that goes into this. We should end up getting something like, let's see here. Yes, 0.78 cosine 40 degrees minus square root 0.78 minus sine squared 40 degrees divided by 0.78 cosine 40 degrees plus square root 0.78 minus sine squared, which you can solve out. I unfortunately solved it for the wrong number in my notes, so I'll ask that you can calculate this. If one of you wouldn't mind volunteering by the next question, we can, if you have a calculator, it's really not that big. What I want to make sure is that you get the concept. The numerical answers are just kind of a side note. But the whole point of this was to find the power reflected in the parallel polarization regime, which we also have a nice that our power reflected percentage-wise for this will be, and this is true for perpendicular polarization as well, the same exact form, is equal to the magnitude of your reflection coefficient squared times 100%. So whatever value this turns out to be, we can calculate the power in the reflected beam just from this equation. And what I assume you should get is a relatively large-ish number. At least that's what I did for this calculations. Those are wrong. So do we have an answer yet? So this value is 0.077, something, right? Okay, cool. So if you were to put this R value into here, what 0.59? You multiplied that by 100? All right. So what this number tells us is that there's really not a lot of power reflected parallel regime, which is very interesting. And that leaves us with the polarization in perpendicular regime. So I'll go ahead and put this up here as a side note so we don't forget our RII 0.077. Let's not forget that, just in case it's. This is for parallel, yes. Does that not look right? Did I miss something? For this problem? Well, oops. In the parallel? Yeah. Yeah, that's why this number didn't really look right to me. Yeah. Interesting. Yeah, it happens. Yeah, when I did it, and I got something like 96%, but that was with the incorrect numbers. So I wonder if, I don't know, I'm not sure. But the setup was correct based off what you did. Okay, the setup is what's most important. Don't worry so much about my calculations here. I did this in like 30 minutes. Like I just threw it together, guys. No, I did get a small. Well, let's just ignore that. Anyway, moving on. Yeah, forget about it. Just follow the formulas, guys.
It's counts, right? Etc.
Is this was this formula? This is for the parallel position. Because this is I grabbed this textbook. Yeah.
Yeah, this perpendicular one.
You did? For the perpendicular, you got a small number. For the perpendicular, I got a larger number. I got a small number parallel and still a small number, but large. This is for perpendicular?
Yeah, you did.
Oh. Oh, okay. Oh. So this is the parallel?
Yeah, it's parallel.
Okay. Very interesting. All right. Let's not get too lost in the weeds. Yes. Well, the next part of this problem was just finding the power reflected in the perpendicular polarization, which has its own nice little formula. Reflection coefficient for perpendicular should be mu2 kz minus mu1 k, yes, ktz divided by mu2 kz plus mu1 ktz. And this is the formula that you should use for this is for parallel. So this is essentially the same. It's plug and chug, guys. There was a third part to this problem, but I seem to have accidentally skimmed over it. If a person is wearing polarized sunglasses, which screen out any light which is polarized horizontally, what percentage of the sunlight power density gets through the glasses? So if it's a horizontally polarized sunglasses, well, all that really means is this is your reflective surface, this is your reflective wave, and here are your boys' sunglasses. And these screen out horizontal waves. This should be, how'd that work? This was the geometry from class. Yes, what percentage of the sunlight power density gets through the glasses if it's light bouncing off of the puddle into the sunglasses? So basically you find how much power is in this reflected ray. You have the parallel and the perpendicular components, and you just omit the perpendicular component. Because the parallel is here, perpendicular is here, and these are horizontally polarized. So that will only let through parallel polarization. The percentages that we solved for? Oh, the reflected power? Yes, yes. So
percentage of
okay, so total power, reflected power. Yes. We calculated the reflected power percentage. So all you have to do is omit one of those components. You should have the answer. I think.
also you have
Well, no, because you have the percentages already. They're in percentages.
yeah, but the percentage of the total reflected.
Oh, you might actually be right. I think it's the percentage of power. No, I'm not sure. So power reflected. I'd have to look back at the textbook. I don't remember exactly these reflection coefficients. Great question though.
I think you have to, because you have the power.
Mm.
Function by
Yeah, because it's just that you're only finding the percentage of that component. Is that right? Because if you know 50%, because sunlight would be, it's unpolarized light. So 50% of its total power is in each one of its components, perpendicular and parallel. So that means 50% of the total power is in the parallel polarization. So you calculate what percentage of that power gets through to your reflected off the surface. So that percentage number, you take that, multiply it by 50%. I mean, it's not quite like that, but you get what I'm saying? Yeah. Yes.
50% of that.
Yes.
You get
The
80 something.
of that power gets reflected.
That
Yes. Yes. And it's the same for perpendicular.
like 20%.
Yes. And then the sum of those two values is the total power that gets reflected, but we only care about the parallel polarization that gets, because that's the only one that's going to get through.
So then you have to
parallel polarization, which is gonna be like. That the,
I think that,
what would be smaller.
I can't remember. I think, yeah.
Are they
The sunglasses? The sunglasses? It says they're. Uh,
have the answer.
oh, you do? Okay.
Cancel horizontal right wave percent power losses 0.2%.
0.292%. So it's a very small number. Yes.
Less than 20% of 50. 20% of 50 gets
Basically, yeah. If what are the numbers on the reflection? The percent, or I should say, the percent power. 0.00584.
Point
0.00584. Oh, it's all that squared. R2 squared. Okay. And that's not times 100%.
not yet.
So in percent, what is that number?
Be half.
Wait, what? Is this? Wait, is this the? Which number? Which quantity is this? Yeah, you might just want to show it to me. Yeah, yeah. Cut out the middleman. Let's take a look here. Oh, through the glasses is 0.292%. Okay. Yes. Huh. Interesting. Huh. Okay. Huh. Yes, I see. So 80. Oh, I see. Maybe, probably. So 88.21% of the total power is in the parallel polarization, and 11.79% of total power is in the perpendicular polarization on the reflected wave. So then, the canceled horizontally polarized wave is the perpendicularly polarized component of the reflected wave. Total percent power reflected that gets through the glasses is 1/2 times that quantity of power, which then is 0.292%. So yeah, basically. I think. Yeah. Seems right to me. Yeah, I think you're right, Nathaniel. Good stuff. Cool. Nathaniel. No problem, brother. Well, that's all the questions I had for this chapter. So it is like, do you guys want to cover any waveguides or anything?
There was a lot of straightforward. A lot of that was plug in.
Yeah. Okay. So.
I just
Yes. Oh, you know now.
I thought it was
Does anyone need me to explain cut? Oh, okay.
it is lower minimum.
It's the lower. So any frequencies lower than the cutoff frequency will, yes, they'll attenuate. They'll operate. The waveguide will be operating in what is referred to as evanescent, which is just exponential decay of the signal. What's that? Huh? Shoot, bro. Go for it.
Oh, you got it. We are cutting off at so that Conlan can go eat.
Yeah. Yeah, you're right.
We're already past 15 minutes, but
Yeah.
that's the question.
Yeah. Yeah, bring it up to me.
Bring it up. At least
Oh, is it really? Let's take a look at it. Which number? 5.31? Consider the coaxial line shown. Yeah, go ahead and erase all of it if you need.
He's right.
Half of the line is filled with air, and half of it is filled with material characterized by epsilon mu1. The electromagnetic wave incident from the left has the fields. Okay. The field of the reflected wave may be expressed as follows. Yes, it gives the waves, or the fields. Write down the fields of the transmitted wave in z greater than 0. What wave number k should be used? Write down the transmitted wave. This is not just a boundary value problem?
It is.
Oh, yeah, okay. And it's going to take long?
Yeah, because you have to get the.
Yes.
And then.
Let's just give a big round of applause to Colin. Thank you very much for doing this.
Hey, next year, you gotta get.
No! We'll see. We'll see.